What?
You say
You mess up your numbers and letters.
yeah, it's like
I always
A,
mess
B,
up my.
C,
But
D, E,
remember, it's
F,
not totally my fault.
Yeah.
It doesn't autocorrect, and I'm not going to go back and redo everything. It just seems like a waste of time. Okay? So this is the last lesson.
C,
Yeah.
A, B, C, 7, J, F, K.
Like we.
Trying to go through. Y and
He's dead.
Let's just skip that then. C, 7, R,
I'll do
U,
Y.
5, 6.
Like Y,
Yeah.
R,
I won't use that one.
Y, R,
Alright.
U, K, H.
Okay, I feel like this is slowly turning into another period that I will remain unnamed. So let's focus. You don't want to be in that category of unnamed period.
I know,
I have a
eighth
question.
hour.
What? No?
I have a question.
That's a name for it.
Are the people who are moving to our class the loud ones? Because if so, no. Why is it?
Can they not?
Were you listening to what I said earlier?
Yes, they're all, it's
Yeah.
Abby and Cassidy.
What about the other? 6.
Good job with the maps.
Alright, there you go. What?
Does it sound like that?
Are you thankful?
He looks like so weird.
Cover your face.
Yep. And how that works.
Oh, I even because he like left a mustache.
Bless you.
Oh, for a while.
Goodness.
I heard there was an interesting thing that happened at the small group party on
Oh yeah.
I wasn't there, I wanted to go, but I was still kind of dealing with the whole strep thing. And they said no kids, and so
Yeah.
that's kind of hard for us.
You could take over my house. I could watch them.
Really? That's what everyone says, but
Yeah.
Yeah.
they're not
They already
that.
have to deal with Henry.
What?
They already have to deal with Henry.
That's true.
What?
Great.
Like every day after school, you dribble this little basketball down to his dad's room.
Oh my word.
It's not little. It's regular size.
Well, okay. Do a size, you, regular size basketball, for a little child.
Lars, like, completely, like, brains out. They used to hurt, so,
What are we talking about?
I was like,
Raised out.
yeah, like, what?
Sydney is confused.
What happened?
Oh my.
Alright,
The mask.
let me begin talking about this. Okay, we kind of used a different word for that. You guys know what word I'm referring to? Communal sharing. Okay? So remember, we have really not talked about the metallic bonds yet. We talked about ionic, it's what we've been doing this whole second half of this chapter. And then the whole first half of this chapter was all dealing with covalent bonds, and we did Lewis structures and all that stuff, right? We really haven't spent any time talking about metallic bonds. And there's a partly a reason for that is because metallic bonds are a little bit goofier and a little bit more difficult to deal with. And they're kind of more very specific general type of bond. And so we're going to take a day to kind of just talk about the basics of it. We're not going to get into doing any structures or anything like that. But we will talk about the basics here. Okay? So, There is, so like we said, what happens with the valence electrons for metallically bonded things is none of them want, right? And what told us that none of them wanted? Okay.
They want to lose electrons.
Okay, yeah, they have a low electronegativity value, so they want to lose electrons, and so they don't have a very strong desire for electrons, but at the same time, if you just got rid of those electrons, you'd have a whole bunch of positively charged ions that would do what to each other? If you got rid of the electrons completely, like completely threw them into some outside source, what would happen to the positively charged metals that were created then? What would they do to each other? They would repel, retract. They would repel each other, yes, kind of. They would repel each other. So, yes, they don't want electrons, and yes, they're doing some sort of sharing, but they're not doing sharing because they want to share, they're doing sharing because they have to share, if that makes sense. Yeah, that kind of sharing, right? It's like, when your brother, you gotta share with your brother, you don't really want to share, but you have to share.
When you drop your Skittles on the floor.
I don't have a brother.
Camilo sharing! Yeah, a perfect example of electrons going equally distributed between all of you guys. That was perfect.
I told you Skittles could be electrons.
Yeah, you're right.
Like the oranges. Kids get to
Okay.
the
So, this idea that the metals don't want their electrons and they're passing them around like a hot potato it's got a name, it's got a theory to it, and it's called the electron seed theory or free electron theory. And the reason why they'll say electron seed theory is because C kind of makes you think of like fluids or things that flow, and that's kind of what happens with their electrons. Their electrons are fluidly flowing in between all the metal cations that are created when electrons are moving or being passed from one to the other. Okay? So, lastly here on this slide, almost all of the metals that are going to be involved in metallic bonding will either have one valence electron or two valence electrons that they're trying to pass away or to share with everybody else. Okay? And that's because it's traditionally the transition metal group that forms these metallic bonds. These guys don't typically form metallic bonds as commonly as the transition elements. And if you guys remember when we talked about valence electrons for transition metals, there was no given trend that we used to figure out how many valence electrons there were. We said they typically have 1 to 2, sometimes 3. Okay? Now, the valence electron theory or the free electron theory is going to lead us to understand a lot of the properties that metals have. I like your electron potluck.
Yeah, communal sharing. Bring 1 or 2 places. And it's free.
Yeah, well,
Electron sharing.
kind of free. Still got to bring something. Alright, this isn't, America or anything. Just show up and get free handouts.
You get it in the mail.
It's like,
Like on the show mail.
credit card. Extra for another one.
Okay. Is there anything you guys can think of off the top of your head about some common properties of metals that you can think of quickly?
They're good conductors of electrons.
Ah, they're great conductors of electricity. Does the theory that we talked about and how metals bond to other metals, does that kind of explain why they would be good conductors of electricity at all? First of all, what is electricity? You guys even know?
It's just like electrons.
Yeah, it's just moving electrons. Okay? Well, what electricity is they create this unbalance of charge, and then when they let those go back to balanced charge, electrons flow, and that creates energy to do work, which we'll talk about energy and work next semester. Okay? But the good conductors of electricity are explained by the electron seed theory, or this idea that these electrons, these valence electrons that they don't want, are freely what? Moving, given, right? Right? If you got these, say you've got two valence electrons and you have one and you have two and you have one and you're all giving electrons, these electrons are being passed back and forth, they're freely what? Moving. Doesn't that create a really good environment for electrical charge to be passed? If you've got already freely moving electrons to begin with? Okay? Also, metals tend to be good conductors of heat. Okay? Well, usually heat is transferred through contact, right? Like if I'm hot and Ethan's cold and I touch him, that's the only way he's going to get my hotness. Okay? Well, same thing happens to something that's metal. If we heat up, like for example, if I've got a pot here, and I'm, heating it up, I'm essentially just heating up this portion of the metal, right? The part that's in contact, correct? Well, what if some electron gets heated up because it's touching that part of the pan, and that electron starts to do what? Move. Transferring energy to the rest of the electrons or pan. Right? Is it possible that electron that got heated up and started moving could come into contact with a metal cation further up in the pan? Transferring its energy, making that warm up? Yes. Okay? Versus if you do this with something that's covalent where the electrons are rigidly held, is there going to be real good transfer of heat or quick transfer of heat? No. It would have to happen very slowly and probably not very well. Okay? So this is kind of one of your rare guys in that metallically bonded things can become stable without fully achieving an octet. If you think about it, if it's not completely giving and it's not completely taking and it's not really completely sharing either, are they getting an octet? No. So, in a weird roundabout way, these guys are achieving stability by this idea that they're transferring these electrons and these fluid flowing electrons are being transferred in between them, in that they don't want them, but they need them to hold the overall thing together. Because if you're a positive metal that lost electrons and you're a positive metal that lost electrons, I need to be what right in between you? I got to be electrons in between you, otherwise what are you two guys going to do? Retract. Yeah, that's going to be our new word. Okay? They're going to repel. So even though I'm moving really quickly, there's probably another free-flowing electron that's probably filling my spot. Right? Okay. All right, and here's just a kind of a vocab word. I'm not going to elaborate too much on this. There is a specific structure that most metallic bonds have, and it's called HCP, or hexagonal close packed. Yeah, I think there's probably a picture in your book somewhere.
I see.
Yep, there it is. What page is that on? 431.
That's too hard to draw. Let's draw.
Well, it's almost impossible to draw 3 dimensions on a 2-dimensional paper without the effects of having it being.
Not if you're an art class.
Well,
3-dimensional.
yeah, but the surface of the paper is 2-dimensional.
No. There's a bunch of atoms that go around, so it's like.
Oh, stop it. You
Art
can't.
would say
Stop
otherwise.
it.
Then you can't turn it into 3D.
Don't you feel bad when you're writing on a piece of paper like you're killing millions and millions of
Well, they're never alive.
I know, but hey, he's a.
That's like,
Yeah,
you
but
feel
atoms
bad
are a
for
little
water.
stronger than
What'd you
Play-Doh.
I mean, that's the same, like, you feel bad for water.
Oh, sorry, Adam. Oops, sorry, Adam.
We're all.
Ah!
Your shirt has a button that's not like button, it's just around.
I hated that one in
What?
particular. The both there's two
That
of them.
section.
There's the top one. They don't
Why do you do that?
There's one
I
that's.
don't see any button on button.
Oh my word.
Just hold it up.
Mr. Kramer, how dare you? Look. I don't like. Oh, great. You were my pant
You
leg
were
halfway
my
up.
favorite teacher. Put your glasses on upside down.
Yes. Don't. Don't. Don't
What are you gonna
fix it.
do about it?
Fix it. Would you create this?
What are you gonna do, man?
Fix it. I don't know if it's my face.
I'll
Fix
fix
your
my
face.
face. That's what I'll do.
Okay. Alright.
Fix your shirt.
So here is your hexagonal closed packed structure. It's actually a structure of 7 atoms. And do you see how if you like kind of like plop them down on each other, like slowly rotate them one spot?
Yeah.
That's what I'm doing.
Tie your shoe.
No.
Tie your shoe.
Roll your sleeve down.
You can run my life.
Administration.
You're not my parents.
Get off my back, Mom. Oh, really, Shane?
Okay. All right, here are, I'll just have to get all these guys in. We're almost done here. I think we might have one more slide.
Finding more colors.
So we've talked about 2 of these properties of metals. There's a 3rd one up here, and I think a 4th one on the next slide. But they almost, yeah, they really, all of these can be explained by really the free electron theory, or the electron sea theory. This idea that these electrons are moving around rapidly, flowing through and in between each other rapidly. The fact that they're loosely held, not rigid, so rigidly held in place, is going to be able to help us explain almost all of the properties that metals, when they bond, exist or exhibit. Except for their ability to retract each other.
I wasn't listening because I like said it in my head. And I realized what you were saying.
What's the matter, Shane?
I don't get what the joke is.
Because I keep saying retract on accident, but
Instead of
the word
repel.
is repel.
Oh.
So I was just like passively aggressively making fun of Sydney. Yeah.
We're making fun of Sydney. I know. Okay.
He's with us now.
Okay.
Is it writing in this hearing what they're saying?
There's like a moment when you're writing your pen and you write down what they said. Oh my gosh, I hate that. Writing your long story and then you out of nowhere. Wow.
Oh, my knees. Sometimes I type that too.
Oh,
Do you
yeah.
have a question, Mari? Why did you raise your hand?
What?
Reflex? Nuh-uh.
Okay. I'll throw some skills at you.
Please
Do it. You're welcome. I'm gonna record it. Oh, not done.
Have I already explained A and B
Yes.
sufficiently enough? Do you think, Derek?
Yeah.
Yeah. Okay, this idea that metals are going to conduct electricity and heat really due to their ability to transfer and allow their electrons to flow really easily. Okay, I don't know if you guys remember this. We did this, right? Did I do the flame test with you guys? And
No.
Yeah.
Yes. It was an
Take
enigmatic.
again.
So if you remember what was going on with that, does anybody remember what was causing the colors to be so different?
The electrons had more energy compared to the up and down energy levels.
Okay, and so when I gave them energy, they jumped up in energy, right? And they jumped to a different energy level, and the light was the result of those electrons being, hey, I'm unstable now. I want to go back to my stable state. And so when they dropped back down to lower energy, they had to get rid of their energy somehow. And so they got rid of their energy in the form of light. Okay? Similar idea here. Because metals have loosely held electrons, they're a lot easier to excite. Okay? So when it says shiny luster, you ever looked at most metals? They tend to be fairly shiny. Or you could say they have a very lustrous look. That's what's really happening is electrons are being excited, and they're constantly being excited and emitting energy in the form of this shiny structure that they appear to be giving off. And so, really, what's happening is when you see, it almost looks reflective, doesn't it? To a certain extent, like when you look at metals, they kind of have a reflective look to it. Okay, what that is just energy being emitted from electrons that got excited and went back down to their lower, more stable energy level. Okay? Well, it's like death week. When you get into college, there's like supposed to be a dead week, but dead week is really just death week. So dead week means you're not supposed to like do anything, or you don't have anything to do, but it ends up being when you have all the tests, because finals are coming up, which means you have to have a test pretty soon before finals.
Are we doing?
I love tests.
Last one here.
No. I put the pencil away. How does space like malleable?
You guys ever heard malleable and ductile before?
I've heard it might have saw it on my vocab sheet earlier today.
Overachiever.
Yeah, real big overachiever. I looked at my vocab sheet.
I just looked at
That's kind of like expected, along with the reading, which no one ever does.
it. We skim.
Yeah, I should go.
Our notes for the answer. Why do you put
You right.
pages, blah, 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 over there? Nobody reads them.
Well, occasionally there's a student diligent enough and good enough to actually do what's expected of them.
I do every other day,
Skim every other day,
depending on what.
Every other-
depending on how long the reading is.
Just wait, it'll get harder.
This is high school, it doesn't have work.
Especially when you.
Middle school was harder than this.
Yeah.
It was harder, like, take 3 for high school, get to high school, wow, this is easy.
Well, that's good. Hey, isn't it? Then our friends got proofs.
I don't know, I don't even remember.
Oh, high school, 3.
Why?
It's
Well,
free. No, it's
so many
thing
things.
costs.
It's
Wait, wait, wait.
hard, you have to like
It's ridiculous.
prove.
I have to make a basket.
Theorem.
Have to make this basket.
So like,
Kind of.
Invest into it.
Okay, can I explain these two things lastly?
Yeah. Yeah.
Okay, so malleable, another word you can kind of replace here that sounds familiar, it's kind of the same idea, is the word pliable. You ever heard of the word pliable? Okay. Like Play-Doh is very pliable. Okay? Believe it or not, metals are very malleable or pliable. I could take a hammer and hit metal and it's not going to cause it to rip or tear. Okay? Dent, but what's happening is when it dents, it's pushing and moving particles around without severing them. However, if I took table salt and hit it with a hammer, it would shatter immediately because ionic compounds are held more rigidly in place. Okay? And ductile means ability to draw metals into wires. Okay? Paperclip, ever heard of one? Yeah.
Yes, I've heard of it.
Okay? We'll talk about, remind me to say a couple more things about this tomorrow. Say a couple more things about this tomorrow. Can you remind me tomorrow to say a couple more things about this?
Maybe, I don't know.
Electron potluck party. I can make a lock pick. Someone can make a periodic table cake. I can make a lock pick and a wrench out of the table cake.